Oh, let me remind you all today, sorry about this, but I've got to take off an hour early from my office. I was gonna give it one because I got a sub for a class for somebody else. Let me know if this is inconvenient and we'll work something out. Any questions from last time? Okay, here's something to look, sort of familiar, I think. Let's suppose, well, A be an R module, and X a subset. And here I even entertain the possibility that X is the empty set. That's possible. Then the module spanned or generated by X is defined to be, well, so actually I'm gonna define it to you this way. I'm gonna say that the module spanned by X or generated by X is the smallest submodule of A that completely contains that set X. Right? So can anybody characterize how it should be defined then? What should be the smallest submodule of A that contains X? How about this? The intersection of all submodules of A such that N contains X. So just take the collection of all submodules that happen to contain the set X. By the way, I know there's at least one, in particular A itself. But just take all the submodules that contain that and intersect them. It's an easy exercise to see that if you have the intersection of an arbitrary intersection of submodules of A is a submodule of A. This is almost exactly like the proof for an arbitrary intersection of subgroups as a subgroup, right? So this is just the intersection of all modules of A. This is the fancy pants kind of mathy way to define it in terms of this intersection. If X well, let me give you a couple special cases, is the union of a bunch of BIs, where each BI is a submodule of A. Then and sometimes we write this as a sum, right? If that X itself is composed of a bunch of submodules that you're putting together. And if I is a finite set, then we've shown, I believe, and it's not the difficult only way to show that if each of these BIs is a submodule of A, then the sum of these, right? Remember, a typical element of this is form B1, B2, Bn with Bi in capital Bi. This is easily seen to be a submodule. It certainly contains zero, just take all the Bi's to be zero. And in fact, we've shown this about abelian groups. And the fact that this is a module follows easily because all the B's are as well. Any questions on this? In general, you might think of so suppose this subset is a collection of elements of A, then a typical element of X is a form R1 X I1 plus R2 X I2 plus RK X IK with Ri and R and Xij and X. So the important thing I think for the takeaway here is this could be a very big set, but what's generated by this, you only take finitely many sums at a time, right? So for example, if this is indexed by the real numbers, you might even have uncountably many generators here in this set. And certainly you would have you have the element Xi in this module generated by X for every I, but you can't ever see infinitely many of them added together at the same time. Right? Everybody clear what I mean there? Everybody okay with that? Okay. By the way, let's look back at the definition too. I did say in the original definition that we entertain the fact that X could be it could be empty. What is the module generated by the empty set? Here, I think it's best to look at our definition here. Zero. That is correct. Which submodules of A contain the empty set? Well, from a set theoretic point of view, any subset contains the empty set, right? So in this situation, what you're looking at is you're looking at the intersection of all R submodules of A, right? And one of them is zero, and zero is contained in every one. So this would be zero. Everybody okay with that? And now we get rid of an embarrassing blemish. How long have we been in algebra now? Everybody's had a semester at least, and then maybe a week. So I guess it's about time we define what an algebra is. Definition. Let R be a commuted ring with one. So that's kind of the base where we start off. R is a commuted ring with one. An R-algebra, remember it all. An R-algebra, say A, is a ring that's not going to be here in this definition, do I? Yes. Now my base here, my starting point is computed ring with one. What is an R-algebra? It is a ring. It doesn't necessarily contain R, but it sort of does in the following sense. A is a ring with identity, equipped with a homomorphism. So it's not just the R, it's not just the A, you need to specify, but there's also a homomorphism from R to A. With number one, F of the identity of R is the identity of A. And two, F of R is contained in the center of A. So in other words, the image of R, the image of R inside this ring here is contained inside the center of the ring. And what I mean by the center of the ring is this is the set of A in A such that all R is a bad choice probably. XA equals AX for all X in A. You might kind of scratch your head and say, well, how do you know that the ring does have a center? Well, certainly, I guess 0 would be in the center of any ring, right? However, we can go farther than that. Under our assumptions, A has to have a center that's more than just the 0 element. You tell me why? What's one thing in A that has to be in the center other than 0? The identity, the additive, or the multiplicative identity has to be in there. So everything that the identity generates has to be in there. So 1 plus 1, whatever that is, 1 plus 1 plus 1. So in other words, there's a copy of Z or Z mod N inside the center, right? So you've at least got that. But what this says is the image of this entire ring in A has to commute with everything in A. Now, I often like to think, okay, here we've defined an R-algebra. You start with commutative ring of identity, and then you have this big thing in a certain sense, this R-algebra A. It's an R-algebra, an algebra over R. Okay, what does it mean? There's a homomorphism from R into big guy that takes the identity, and the image of R is in the center. Can anybody tell me what this is probably mimicking, or can somebody tell me something familiar this mimics? Anybody know what they're trying to do with algebras? They're generalizing something, perhaps.
Is that a generalization of scalar multiplication?
Oh, you're getting close. You're getting close, Neil, but you need to believe. So anybody want to guess if I start with like Z, what's a good example of a Z algebra? Well, somebody can give me the smart aleck example. How about Z itself, right? Okay, so if you look at this definition, certainly if you start with commutative ring of identity, you could take that you could take A to be R and that homomorphism just to be the identity, right? So any ring is a commutative ring of identity is an algebra over itself. But how about an algebra over Z that is not commutative? There you go. I don't need to tell you what the matrix is, you have to experience it for yourself. So here's an example. Here I generalize Z a little bit. Any commutative ring of identity, you can look at anybody in matrices over R. That's a ring. It's not commutative if N is at least 2, right? And what would the homomorphism be? F from R into A at F of R equals, better be a matrix.
R0, 0, 1.
Well, right.
Yeah. So,
Right. And of course, notice the diagonal matrices, which is, oh, no, that's not the right terminology. The scalar matrices, like this, are in the center. They commute with every matrix, right? Okay, any questions on that? Let me give you a proposition here. Well, I'll just say a couple things about all of those. So proposition. 12, 1 something, 16. If R, if A is an R-algebra, then okay, so let me do this quick little. So this is actually, even though this might seem kind of silly, this shows you kind of how to ramp things up, and this is useful oftentimes. Okay, suppose I have an R algebra A. I want to turn that into a module, right? So right out of the gate, I need to define our multiplication from R. Right, so let R be an R and A be in our algebra. Now I want this to be an R. I want this to be an R module. So I need this to somehow barf out something into something in A. How do I multiply something by R and something by A? Okay, that's right. Let's use the homomorphism, right? Because the easiest thing is, I wish R was in A, maybe it's not, but what I can do is define this to be F of R times A. And notice that F of R is an element of A, so this multiplication makes sense. Now, I guess I need to verify that this works the way I want it to work. So if let's go here, R1 plus R2 acting on A. Well, this is F of R1 plus R2 multiplied by A. But F is a ring homomorphism. Let me clarify that here. Yeah. So I guess that was the first. Yeah. Okay. R and A are rings, so of course this is F is a ring homomorphism. This is equal to F of R1 plus F of R2 times A, because that's what that is. And now multiply this through. Which equals R1A, R2. Everybody cool with it? Okay, 2. R1, R2 acting on A. Well, by definition, this is F of R1, R2. multiplied by A, because now this has been promoted to being an A. And this is a ring homomorphism, so I can break that up. Right? And since these are all elements of A, I've got associativity, so I can do that mess. Okie dokie so far? And let's see, am I ready to unpack this? This is FR1, and this is, by definition, R2 acting on A. And of course, this is an element of A that this is acting on, so this is R1, R2. Okay. Most triumph. And 3 R, again, by definition, this is F of R, A1 plus A2. These are all elements of the same ring, so I can distribute. R, A1. Okay, so there you go. So this turns, this structure makes this an R module. Okay. Any questions?
Dr. Carter?
Mm-hmm.
So can we understand the R-algebra to just be, like a ring with scalar multiplication defined on it?
Well, I mean, well, yes, and in fact, that's what this shows. Because the scalar multiplication is just this right here. Right, that's essentially what you're doing. Okay, other questions? All right. How about, okay, so here's the left definition. We've defined algebras, so I need to tell you a little bit about their morphisms. Definition 12.18. Suppose that A and B are R-algebras. So what does it mean to be an R-algebra homomorphism? B from A to B. Well, first and foremost, these algebras are rings, so it's going to be a ring homomorphism. Such that, number one, I demand that phi of the identity of A is the identity of B. So you got that going for it. And number two, it's an R module homomorphism in a certain sense, in the following sense. Phi of RA is R phi of A for all R and R, A and A. And let me be very careful about this here. When I say R times A, what do I mean? I mean it in the sense of the previous proposition, right? That's the way that we multiply there. Okay, any questions?
So for R, it's just like any ring that takes it to like
Any commutative ring.
any community ring. Okay.
Right. Yeah, and of course, again, one of the reasons I brought up this generalizes matrices is to this day, if somebody starts talking about algebras, the first thing that'll pop into my head is, okay, it's like some generalization of a matrix ring, because that's essentially what it is. To a certain sense. Okay, so here we're going to talk about quotient structures a little bit. As you might guess, just like you have before. Quotient structures. And homomorphism theorems. Once again, we're going to have this kind of repeating theme. So you're going to see a lot of stuff that's kind of familiar, I think, that you've seen before. I'm just going to hit this right off. Theorem 12.2.1. Let B, C, and A be our submodules. So implicitly, A, B, and C are all R modules, and B and C are submodules of A. The quotient group, A mod B, no, parentheses, let me write this out here. The quotient group, A mod B. Okay, well, so of course, here we're talking, since these are R modules, we're talking about abelian groups here. So we know that A mod B is an abelian group. This quotient group makes sense because all subgroups are normal. With action given by so for me to turn this abelian group into an R module, I have to intelligently tell you how to multiply by an element of the ring. Okay, output should be plus B, right? Because the output is always also got to be an element of the quotient group. What's the easiest thing you can think of that goes right here? Most natural thing, if you will. How about RA? There you go. The map, pi B. Map pi B from A to A mod B. This is sometimes called the natural or canonical projection, given by pi B of A. By the way, this is the similar idea to where reducing mod B, right? If I say what's 27 mod 5, right? It will be 27 plus 5K, which you could reduce to 2 plus 5K, right? That's what this thing does, it's reduction mod B. Is an R module epimorphism. So it's on to with kernel. Anybody want to guess what kernel this is? B. Oh, right, I did. There is an R module homomorphism, isomorphism. Um. And finally, if so, I started out by assuming that B and C are just two random submodules. If so, we have C and B and A. I'll just clarify that. Then, then B mod C is a submodule of A mod C, and their quotient. So since this is a submodule of this, you can quotient out A mod C modulo B mod C is isomorphic to A mod B. So this is reminiscent of the second, third isomorphism theorems. I will do the first one too. Who wants to see this proof? Maybe I should start this off. Don't be shy. This is your class too, right? I mean, let me do at least a little bit of it, right? But what you'll see here is there's. How many of y'all recognize this from what you did in 4120? Only it was in the context of groups, right? Group perhaps. Well, it's the same crap, but the difference is we need to sort of convince ourselves that all the homomorphisms that are going on aren't just Abelian group homomorphisms, but they're honest to goodness R-module homomorphisms as well. So, and also we need to know that that R action that I defined in 1, this is always the big thing, right? I made this claim that this is my R action, and it's pretty easy to prove that this turns this into a R module if the action is defined in the first place, is well defined in the first place, right? Because I could have multiple cosets of A plus B, and this may not be well defined, so we need to check that. So let me highlight some proof. So number one, I want to show that that the action is well defined. I mean, otherwise I'm in a load of trouble. So let's suppose A plus B equals A prime plus B. So suppose I have two different representatives of the same coset. Because A and A prime represent the same coset, what do I know about the difference between A and A prime? It must be in B, right? They're sort of equivalent mod B, so their difference must be in B. Okay, therefore, R since A and A prime are in B, and B is a submodule of A, R times A minus A prime must be in B because the submodule is vacuum cleaner. Therefore, RA minus RA prime is in B. Multiplying that sucker out. Therefore, RA plus B equals R A prime. So, well defined. Okay, good. So at least my R model actually makes sense. It's a well-defined action. Now I need to show all the stuff about modules. Are you guys okay with me skipping that? Like that R equals R2 times this follows this rule. Everybody okay with that? Okay, the well-defined, this was a big thing. This, let's look at 2. Notice that notice pi b of this is this. So that shows it's an abelian group homomorphism. All right, so I'm halfway there. And notice that pi b times RA is RA plus B. Now I've proved that this is a well-defined R module thing, so this is times so pi b is an R module homomorphism. Notice that if A plus B is in A mod B, then A plus B is IB of A. So epimorphism. And finally, I'll talk you through the kernel of B part. Notice that if you start with something in B here, then this is little b plus big B, which is the same thing as 0 plus B, right? So if you start with something in B, then it's in the kernel. So, right, so B is contained in the kernel. On the other hand, if A plus B is in the kernel, that means A plus B is 0 plus B, which means A minus 0 is in B, so A is in B. Everybody okay with that? Okay, now we've got these other statements here. Maybe I want to come back to these after the. So. To do part C and D, the easiest tack is to do the next theorem, which actually, I put in as first isomorphism theorem. It's the analog of the first isomorphism theorem for, modules. So I'll leave C and D, see if you can work through that, because it's C and D is, again, like I said, the proof should be exactly the same as you saw in even the abelian group theory part. The only thing you have to do is consider your, the homomorphisms that you get are module homomorphisms. And after I do the first isomorphism theorem, I'll outline it for you. Theorem 12.2.2. Let F from A to B the, and homomorphism homomorphism. Then F induces an R modular isomorphism. Isomorphism. F bar from A mod kernel of F to the inverse F. And in fact, I'll say, here's the way it's defined. Your input is one of these cosets here, A plus kernel of F, and your output is F. Using the original map. I'm gonna, in case some of you didn't see these details or it's been a while for you, I will go through at least the beginning part of this. The theme here is very much, it's similar to what we did before, where the heavy lifting of this is not showing that you have isomorphism. That actually is fairly easy following the setup that F is an R modular isomorphism. The heavy lifting is showing that freaking F bar is a function in the first place, right? That's really the hard part, is just showing that this thing is actually a bona fide, well-defined function. So, yes, we have a no tolerance policy here. Look at this. So, proof. First of all, we need F bar to be a function. So, okay, so let's suppose A plus kernel of F is equal to A prime plus kernel of F. So remember, of course, the kernel of F is a submodule of A, and these are just two cosets. Right? Just like before, this means that the difference of A and A prime must be in the kernel of F. Therefore, F of A minus A prime must be 0. So we have F of A minus F of A prime is equal to 0. Or therefore, F prime is well defined. Because what this says is, it doesn't matter if you use the representative A plus kernel of F or A prime plus kernel of F, your F of A prime give you the same thing here. Right? So there you go. Now that you know it's a function, the rest of it from here is kind of downhill. So why is this an R module homomorphism? Well, F of A plus A prime, or F bar, oops, sloppy, kernel of F, A prime, kernel of F. This is F bar of A plus A prime plus kernel of F which by the definition here is f of a plus a prime, which is f of a plus f of a prime, which is f bar of a plus kernel of f plus f bar a prime plus kernel of f. So abelian group homomorphism, got that way. Next task is to worry about the scalar multiplication part. F of R if you look at this here, this is that's f of, that's a little hard to read, isn't it? F of RA plus kernel of M, which by definition is F of RA, which now F is our friendly neighborhood R modular homomorphism. So now I can slide the R out of that. And this is R F bar of A plus kernel of F. And there you go. So it's an R modular homomorphism. So this thing, well-defined R modular homomorphism, it's clearly a Hum2, right? Because the image is exactly what you're going to get here, right? Because every possible f of a is in the image, right? And f bar is onto as image of f bar equals f of a, which is an image of f. I guess the last thing is why is this 1-to-1? Well, killing the kernel actually did it for us. This is why it's 1-to-1. Let me mop that up a little bit. Suppose a plus kernel of f is in the kernel of f bar. Right? This implies that f of a is equal to 0. Therefore, a is in the kernel of f bar, or I'm sorry, in the kernel of f. So a plus kernel of f, 0 plus kernel of f. Therefore, f bar is 1-to-1. So that's it, pretty much in complete detail, I think. And so, for example, for part C, I'll just kind of give you sort of a running start at this. If you want to reconvince yourself for the R module case, part C, let's say F from, I guess, B to B plus C mod C. Let me give you kind of a simple one here. Well, I guess there is a class after us, so maybe I should check with them. Okay, here's Jim's hillbilly homomorphism from B to B plus C, because it's the easiest thing I can think of. Input B, oh, how about this? B plus 0 mod C, right? Like that. Verify that this is a R module homomorphism, not too bad. Verify that this is an onto, that's also not so bad. And this is an onto R module homomorphism. And the kernel of F Well. Can you all see what the kernel there has to be here? This B plus 0, this B has to be actually in C. Agreed? So the kernel that turns out, it's easy to verify, is B intersects C. Now apply the first isomorphism theorem that we just proved. This is onto, and the kernel of this map is B intersects C. So this mod this is isomorphic to this. All right. That's just one piece of it, but see if you can get through that. Any questions? Okay, well, you all have a good one, and we will see you next time.